This problem is very similar to the previous one. We have a person holding a bag. This time the bag is on the same side as the leg they're standing on. Suppose you're holding this bag, right? And that changes our diagram a little bit, because if you remember from the previous one, the weight of the bag was way over here. This time the weight of the bag is over on the same side as the foot, right? So we got the midline, we've got the foot, we got the bag. Now, in the end, it's on the same side of the body as the hip, would be a better way to put it. So again, this is another statics problem. All right, so we have the sum of the forces is 0, the sum of the torques is 0. As with the previous problem, we're going to start with what are the external vertical forces. Again, the forces here on the hip are all internal to the body, so we're taking the macro view of the whole body, and what do we get? So vertical forces calling up, positive, we have the normal force minus the weight of the person minus the weight of the bag equals 0. And, from our nomenclature we had before, where the weight of the bag is alpha times the weight, we're just going to call this the normal force then is 1 plus alpha onto the weight of the person. Again, we don't know the weight of the person, but we're going to find out we don't need to know the weight of the person to figure out everything we need to know, because we're expressing this in terms of a factor times the weight, right? The weight's just an overall normalization factor. All right, so this turns out to be exactly what we got before, and it makes complete sense. We're not talking about rotation or anything like that. We're just talking about straight up what is the normal force, right? Which has to be the sum of all the weights going down. Okay, the next piece though is what is this distance x? All right, and for that we're going to use the torque. And remember, if we look at the midline, right, as a pivot point, the normal force now as drawn is going to cause a rotation that way, and the weight of the bag is going to cause a rotation that way. Those two have to cancel out. The clockwise is negative, the counterclockwise is positive, and so we're going to start with the positive one, which is the distance the bag is from the midline times the weight of the bag minus the distance the normal force is from the midline times the normal force equals 0. Well, we know the normal force is 1 plus alpha times the weight. We know the weight of the bag is alpha times the weight. So this is alpha times the weight minus, okay, x times 1 plus alpha times the weight equals 0. You'll see again the weight cancels out. And we've got x in this case is going to be x equals alpha over 1 plus alpha. Now this looks exactly times x back. This looks exactly like what we had before, the exception being that in the previous problem it was on the other side of the midline. In this problem, it's on this side of the midline, right? It's on the same side. Well, in both cases, it ends up on the same side as the bag because it has to counter the torque, right? The formula ends up being the same, but it's closer to the hip instead of farther away from the hip. So that's our macro view. And now we need to zoom in. Now that we have what n is and we have what x is, we need to zoom in and we need to look at the leg itself. And so we're going through a very similar process to what we had before. We're looking at what are all the vertical forces in the leg, what are all the horizontal forces in the leg, and what's the torque. We're going to start with the torque this time because we discovered last time we had to take the torque to find the force F. We had to calculate the torque to find the force F. And so we'll start with what are our positive torques, right? What are our positive torques? To find out our positive torques and our negative torques, and we know F is going to be a negative torque, right? We know F is going to cause a negative torque because it causes rotation that way. We know the normal force is going to cause a positive torque because it causes a rotation that way, potentially, right? And here's why I say potentially. We need to know where the normal force is, right? We need to know where the normal force is. And so and we need to know based on where the normal force is, where the center of mass of the leg is, right? So the normal force with respect to the pivot point at the um, hip, right? Normal force with respect to the pivot point at the hip, we can say it is the distance from the normal force to the hip is going to be x, I'll call it xo. Xo is going to be x mid, right, minus x hip minus x. Now, depending on what x is, right, let's put in what x is. So x on is x mid minus x hip minus, and x was alpha over 1 plus alpha onto x bag. So x naught, all right, x naught might be negative, right? X naught might be negative because depending on how, we know x mid minus x hip is positive, but depending on how heavy the bag is and how far out the bag is being held, x naught might be negative. Well, because that sign takes care of everything, we can simply plug it in, all right? We know the distance between here and there. Now, what's the distance between the center point on the leg and the pivot point? And I'll call that x leg. All right, what is that distance? Well, x leg is, first, it's got to be 1/2 of what? X mid minus x, right? So x mid minus x gets us to, x mid minus x is right here. Half of that gets us to there, all right? And if we assume for the moment that since our positive x direction is to the right, that's greater than x hip, then we subtract out x hip and we have how far away the center of mass of the leg is from the pivot point at the hip. All right. Okay. If it ends up on the other side, this number ends up being negative, and we're good because the sign takes care of the problem. So let's put everything together. We're going to, for the moment, because it's drawn, we're going to assume that's positive. We're going to assume that's positive. If those are positive, this one is causing a positive rotation. This one is causing a negative rotation, and this one's causing a negative rotation. So we're going to start with our positive rotation. N times the distance N is from the center of rotation on the hip minus the center of mass of the leg, which is going to be times the force there, which is 1/7 of the weight, minus F times the distance from F to the center. And all of that has to add to 0. So far, so good. All of this has to add to 0. All right. So now we have everything we need to calculate F, because we know everything in X naught, we know X leg, we know N, we know W, we know everything we need to calculate F. And then when we go to look at, okay, so from the torque, right? This is from the torque. When we go to look at vertical, vertical is very similar to last time. I'm going to just call it Fy minus Ry minus 1/7 W plus N equals 0. And then horizontal, we have Fx minus Rx equals 0. And that's it. And of course, Fy is F sine 70 degrees. Fx is F cosine 70 degrees. Hopefully this will get you through the second problem about the hip.